Hi guys, for today's video, we are going to discuss the application of first order differential equation in electrical circuits using RL and RC circuits. Here, first, you must be familiarized the things to remember in RL circuits or what are the things you can see to identify the circuit is an RL. First, there is a resistance present in ohms, I or rather current in amperes, L stated as inductance in henries, E voltage source in volts. Here is the example of the simple RL circuits. Here you can notice the four major components of an RL circuit is present here in the circuit. V for voltage sources, I is for the current, R is for the resistor or resistance, L is for inductance. By Ohm's law, you can compute the voltage drop in the resistor by getting the ampere flow in the resistor and the resistance present in the resistor. But to get the voltage drop in inductance, you must get the inductance first, multiply it by di over dt. How to derive the formula for each component in voltage drop? First, we start in inductor. Get the inductance, multiply by di over dt as said earlier, and here you can get the formula for each voltage drop. Resistor, as stated earlier, get the ampere or the current present, then multiply by the R or resistance and combine it. Then you can get the voltage drop of the resistor. The capacitor is simply 1 over C multiplied by Q or charge and combine it. Here is the example number 1, which stated as determine for a differential equation for the current I with respect to T if the resistance is R, the inductance is L, and the impedance voltage is ET or otherwise known as voltage total of the circuits. Here is the circuit given where we can visualize the three present. First, by Kirchhoff's second law, the second law states that the voltage total of a circuit is equals to the sum of each voltage drop of the component present in the circuit. Hence, we can use that L times di over dt plus IR equals V. Then we multiply it by L, 1 over L to cancel the L to get us a linear or differential equation. Our differential equation now is di over dt plus IR over L equals V over L. We can get the integrating factor by the means of E raised to integral of dt dt, because this one is the same as y prime plus p of x y equals q x y. Here I write it. It is as the same as, because the y prime is same as, the y prime is the same as di over dt or dx over dy, depending on the independent and dependent variable present in the equation. We can get the if or the integrating factor by the means of raising it to e integral of dt, which in the equation here we can get it here dt. RL, the second one is e integral of RL dt. RL because the I we can remove it and move it as a constant. The integral of RL dt is equals to e raised to RT over L. Next, Here we can get a linear equation. I times IF equals integral of integrating factor EL dt. We substitute the integrating factor here. I times E raised to RT over L equals V over L, because the V over L here, or E over L, is constant, and the remaining is integrating factor and the dt. Integrating factor, here we substitute it and times it by dt. We multiply it by 1 over ERT over L to remove and to let the I remain in that side. Here we can cancel it. I is the only one remain. Cross multiply, cancel it. VR is the only remaining. E over RT L. E over RTL, we can cancel it. The remaining is C over E. E equals E over negative RT over L. It becomes negative because here it is in the denominator side. When we go it to the up or to the numerator side, the sign will change because of its changes. When I0 equals 0, here is the initial condition 0, and we use this formula and substitute the initial condition. I is equals to 0, V over C R plus E raised to R 0, because this is 0, L. Hence the C is equals to V over R, and then we can use it. I was V over R minus V over R E minus RT over L. We can factor out V over R here in both sides, and our final answer will be V over R times 1 minus E raised to E raised to negative RT over L.
Johnny.
Yes, Papa.
Eating sugar.
No, Papa.
Telling lies.
No, Papa.
Open your mouth.
And now, we're gonna talk about RC circuits. Of course, if there is things to remember in RL, there is also things to remember in RC circuits. There is also a resistance, current, but there is a capacitance present in RC circuits, voltage surge in volts. This is an example of simple RC circuits. Here, we are given an exercise to determine a differential equation for the charge Q of t on the capacitor if the resistor is R, the capacitance is C, and the impressed voltage is ET. Here is the circuit. Where VR equals IR, VC equals QC, I equals DQ over DT. First, we get the total voltage across the circuits. So we just add the VR plus VC because there are only two components. We substitute the formula VR equals IR, then IR, plus VC equals QC equals V, capital V. Then we notice I is equals to DQ over DT, then DQ over DT is present here times R plus QC over V. We have to remove the R to get us a differential equation, so we have to multiply the whole equation to the I1 over R to cancel out the R in the other side. So the only remain will be dq over dt plus q over rc equals v over r. The same as y prime plus qc, y prime plus pxy equals qxy. Then we get the integrating factor of this equation, e raised to integral of pt over dt. The p here is 1 over rc because the q can be a constant. The integral of 1 over rc dt equals e raised to t over rc. Now we proceed to the formula of q integration factor equals the integral of integrating factor qt dt. We substitute all the value present here. Qt, this is the Qt. Then we put the V over R here because it is a constant present in this equation. Now, we are going to integrate this. This will result to RC e raised to t over RC, and because you integrate, you just have to add an arbitrary constant c. Here we can cancel out the r, cancel out. The only remaining will be vc raised to t over rc plus c1. We just have to multiply the whole equation to 1 over et over rc to remove this, and the q will be the remaining variable in the left side. Q equals vc plus c1 e raised to negative t over rc. It becomes negative because we put it to the top and we change the sign. Now, given the initial condition, here we have our initial condition, we are going to use this formula. Q equals vc plus c1 e raised to t over rc. Substitute all the present. 0 equals vc plus c1 e negative t over rc. Negative t equals to 0, so we just have to e raised to 1. E raised to 0 is equals to 1, so we don't have to put it plus 1 here. C1 becomes equals to negative vc, then vc becomes negative because we move it to the other side. Now we just have to simplify it to get the general solution for the RC circuits. Q equals vc minus vc e raised to negative t over rc, or simply as Q equals vc times 1 minus e raised to negative t over rc. Here we get our general solution for RC circuits. Thank you.
It's been a long day without you, my friend. I'll tell you all about it when I see you again.
Sa kami na ang mutuka, tao bastang dagdag. Gago!